All right, hello. My name is Aaron. I don't have any grad student. I am the grad student of Rachel Summerfield. And I need to stop this thing from playing by itself. Okay, well, I hope it doesn't. Okay. Is it playing? Okay, anyway, cool. All right, so today I'm going to tell you about the UV luminosity functions at z greater than 6 predicted by our semi-analytic models and their implications for cosmic reionization. All right, let me just bring this out of the way. Okay, so from a number of observations, we know that the universe is ionized. And so on the right are the modeled and observational constraints on reionization. And we know that happened roughly around 10-ish to 4-ish. And we will compare some of our results with some of these constraints later. So far, there isn't any conclusive theory that explains exactly how this happened and what made this happen. And we ask, can galaxies be the one that ionized the universe? And let's look at the diagram on the left. It is a study from Frankenstein et al. 2015, plotting the UV-specific luminosity density versus redshift. And the gray bands here indicates the density needed to sustain a fully ionized universe. And for 4 different scenarios, as you go down, the requirements slightly loosen, so it requires a higher UV escape fraction and a lower clumping factor, meaning the universe gets recombined slower as you go down to the lower bands. Anyway, so the observationally determined density functions are plotted in blue and cyan, which the blue includes all the galaxies down to -13 of magnitude, and the cyan ones only includes galaxies that is down to 15% of the completion limit. But either way, just by comparing these data points to the blue line, which is their traditional model, the thin blue line underneath the second band, we can see that the galaxies detected to date cannot sustain a fully ionized universe. And we can safely say that under the current detection limits, galaxies detected to date are insufficient to reionize the universe. So, maybe the key to the solution of the problem lies in galaxies population that are currently undetectable. And we asked the follow-up question, were these galaxies below the current detection limits able to reionize the universe? And the answer is yes. Some studies, for example, the one by Coulon and Fauché-Giguère, extrapolate this population from current observations, and as seen in the diagram on the left. And their calculations, as shown on the right, show that these faint galaxies can indeed ionize the universe in a timely manner. So the remaining question is, can the current galaxy formation models predict this population? Or, in other words, do we know how to make these galaxies? The early universe is dominated by low-mass halos in the range captured in this diagram. However, as these z equals 0 abundance matching constraints reviewed, low-mass halos are quite inefficient. They're not good at making stars, and some of them even fail to make stars at all. So star formation's efficiency within this halo appear to be the key to the solution and the key to accurately modeled reionization. So apparently, there is a tension in star formation efficiency in this low-mass halo in between high and low redshift, which we want them to be more efficient at high redshift, so they produce enough stars and galaxies to reionize the universe, but later become less efficient, so they don't overproduce stars and galaxies that we don't see in the local universe. So to reconcile the tension, we are putting together a streamlined model that keeps track on both galaxy formation and cosmic reionization, and we want to see if our model can simultaneously satisfy constraints at all redshifts. So the following is a brief outline of our approach. We obtained our sample galaxy population from across a wide range of redshift from our SAMs. And then we apply the SAM's output to an analytic reionization model, which allows us to efficiently forecast the cosmic reionization history. And then we will compose both the SAMs and the reionization model to an MCMC machinery, which allows us to systematically explore the parameter space. And after that is done, we will build and compare our result with a self-consistent, high-resolution numerical simulation for reionization. And using that, we'll be able to provide useful forecasts for upcoming high-redshift observations. So why do we use SAMs? SAMs are by far the most computationally way to obtain a large galaxy sample. It can easily handle hundreds of thousands of halos, or even up to millions of halos. And it can And they're able to achieve very high mass resolution in large volume, with resolution down to the atomic cooling limit, while simultaneously tracking many physical processes efficiently. And this allows SAMs to run on a large volume with sufficient resolution all the way down to the local z=0 universe, which most numerical simulations find difficult. And its efficiency also makes it an excellent tool for probing the parameter space. So I know most of you know how SAM work, but do allow me to give an ultra brief recap for people who are not familiar with SAMs. So SAMs use dark matter halo merger tree extracted from high-resolution numerical simulations, just like the one shown in the lower right-hand corner. And then the model tracks the physical properties of these galaxies inside these halos with either analytic formulae or empirical recipes that can be calibrated to observations. So we are using two different SAMs in our project, one from Rachel Somerville and one from Yulu, who is currently a postdoc at Carnegie Observatory. The Somerville model includes many standard recipes like cosmological gas accretion and cooling, stellar feedback, stellar-driven winds, and many others. And we also use the two following models to compute the spectral evolution of stellar population inside these galaxies and to account for attenuation by dust. Here I want to highlight two more recipes that are updated in the latest model, which play significant roles in our predictions. With these new recipes in place, the model now tracks the formation of molecular hydrogen, and it employs a molecular hydrogen-based empirical star formation recipes. And we believe that with these new recipes in place, it can give more physically motivated predictions and enhance the accuracy of high redshift predictions. All right, so the other SAM we use is developed by Yulu, which the model is known for its deep integration with the powerful MCMC machinery. It is designed to systematically explore the large parameter space under available observational constraints. This diagram demonstrates the output of the LU model in comparison to other traditional SAMs. The contour shows the posterior probability density from the LU model output over thousands of iterations, which maps the correlation between the input stellar feedback parameter, or beta, and the faint end slope of the output luminosity functions, alpha. As the contour demonstrates, the bigger the feedback parameter is, the more effectively get pushed away by stellar winds in smaller halos, and leading to a shallower faint end slope, and meaning that there are fewer faint galaxies. And in contrast, the Somerville model indicates by the blue star is calibrated by hand and only spits out one output at a time. So here you have all the backgrounds, and I think we can get into the results. So here are the luminosity functions predicted by SAMs at redshift 6, 7, 8, and 10. The blue solid line here is predicted by the Somerville model, and the purple line is from the LU model. Note that both models are calibrated to the same observational constraint from the local universe, but with slightly different choice of physical parameters. So for details of the comparison, you can go back to the 2014 paper by Liu et al. You can see that the two models disagree on the faint populations, which suggests, so on one hand, the Somerville model suggests a larger faint population, and the LU model says otherwise. And we think this discrepancy mainly arises from the choice of stellar feedback parameter. And quick flashback, the choice of stellar feedback parameter in the LU model is higher than the Somerville model, which implies more efficient stellar feedback and less efficient star formation inside this halo. And this really leads back to our question, do we know how to make these galaxies, or is there even this faint population? So to check our results, we compare them to a number of observations shown by the dark marker, including the latest Livermore 2016 result. It's a little hard to spot, but you probably know where they are. And with high-resolution hydrodynamic simulations shown by the red and green dashed lines, even though this is only calibrated to the z=0 universe, the result from the Somerville model seems to be in great agreement with other studies. And this looks very promising, I think. I also want to point out that we actually made these predictions before the frontier field observation comes out. So it is very encouraging to see that the SAMs and the frontier field observation actually support each other. And I think this is quite promising as well. So I also want to point out that in this particular run, we have turned off the effects of photoionization feedback, also known as squelching. Recently, there are more and more evidences showing that the effects might be weaker than we thought. And our results support this given that they're good agreement with the hydro simulation, which they treated squelching self-consistently with embedded radiative transport. And overall, our predictions show great agreement with other studies, and we are very excited to see this. And we plan to further improve this by fine-tuning the model parameters using the LUM model. All right. So after making these predictions, we are going to feed these luminosity functions into an analytic reionization model, like the one documented in that paper. Just to give you a sense of what it does, here are a few important equations of the model. First, we have the reionization equations, which says the ionized volume of the universe will grow with the supply of the ionizing photons, which is in the first term known as the source term. And the growth is resisted by the recombination of ionized hydrogen, which is in the second term known as the sink term. So solving the differential equation will give us a general volume average to evolution of the ionized volume as a function of redshift. And we can calculate the Thomson optical depth by integrating the volume filling fraction. And just to test drive the model, we ran it with an array of constant UV escape fraction and compared them to some observational constraint. And yes, we are treating it as a constant for now. All right. So here are some of the model outputs. On the left, we're looking at the evolution of the neutral volume fraction as a function of redshift, which gives each with a different escape fraction color-coded as says in the legend. And look like the galaxy population predicted by our SAMs can surely reionize the universe regardless of the choice of UV escape fraction between that range. And then expected, the more photons are able to make their way out, the faster the universe get ionized. That's obvious. And using this result, we also calculated the Thomson's optical depth, which is shown on the right. And we find that with each escape fraction around 1.1, the optical depth best agree with the Planck 2015 measurement, which is also in agreement with many other theoretical studies. So coming up next, we will use the LUM model to explore the parameter space. Again, the LUM model is coupled to an MCMC machinery, so we can systematically explore the parameter space and gradually improve its agreement with the observations. So on the left is something very similar to what we have seen earlier, and I'm going to talk about the one on the right. So again, it correlates the Thomson optical depth to the input stellar feedback parameter. So you can see that in the LUM model, even though with very low feedback parameter, it's still only barely teaching the results reported by Planck 2015. So we expect that the feedback effect should be maybe smaller. Or we have to do other treatment to that recipe. So for upcoming work, we plan to use the LUM model to explore the parameter space again and seek for the set of best fit physical parameter. Perhaps we'll need to adopt a more physically motivated treatment for stellar feedback that based on more physical properties of the halo in galaxies, such as metallicity and chemical enrichment. And by doing so, we hope this will lead to more effective stellar redshift evolution for star formation efficiency. And we're also going to vary the UV escape fraction based on galaxy properties, physical properties, using results from high-resolution numerical simulations, just like the one from Phoebe. In fact, we have been talking to John Peter. So on the other hand, we will need to create a self-consistent treatment of reionization for our SAMs to replace the current instantaneous treatment, and which will be a high-resolution hydrodynamic simulation. And with the advantage of having a large galaxy population provided by SAMs, we will be able to provide a physically accurate reionization simulation. And from there, we can offer forecasts for future observations, like maps of H1 intensity and the topography of reionization. I think I'll conclude here.
I probably missed it, but you posed a very interesting question at the beginning where you said that dwarf galaxies at high redshift have similar mass system to the dwarf galaxies we see today, but they must be fundamentally different because they clearly evolve differently and of course merge into more massive galaxies. And I didn't, maybe I missed, but I don't know whether you actually answered the question. And I want to also add a comment, which was to the black hole talks earlier today, which I think have exactly the same problem. If you seed all of your galaxies with black holes, you're inconsistent with the lack of black holes in some low-mass galaxies today. And so I was just curious whether you had a comment on this.
So we can't answer the questions yet, but we do know, we do have a plan. So again, we plan to implement like a more redshift dependent, or not redshift dependent, but more physically motivated treatment for the feedback effect. Because we think right now the treatment for feedback is kind of simple. We are using this equation on the top, which only depends on 2 parameters, but it doesn't account for something like metallicity and chemical enrichment, so that will also affect the efficiency for star formation inside these halos. Right, I think. Slate.